Okay, I start now. I'm here on behalf of Isabel Lima. She led this study about magnetic accretion in SW sextant stars. So Claudia already did a nice introduction about cataclysmic variables. And she mentioned that most of them, they have accretion disk, and that's the main transfer process in cataclysmic variables. And when the white dwarf is a magnetic system, then we can have accretion column. This accretion column can disrupt the disk totally or just partially. So in some objects, you have the accretion disk, and then you still have some magnetic effects in the close to the white dwarf. But talking about SW sextants and classification, so here I'm going to talk about some of the relevant classification. That's the dwarf nova systems. When you have the variability of them comes from the disk changing from a bright state when the matter is falling to the disk, and quiescent state when the disk is just building up matter. And we have also the nova and the recurrent nova. In that case, the variability comes from thermonuclear reactions on the white dwarf surface with material that build up on the surface. And we have the nova-like systems. That the name can imply that they are like the nova, but they are actually like the dwarf novas. And they are like dwarf novas that are always in the eruptive state. They don't show quiescent state. And the SW sextants are one of them. So they have this huge bright disk that's always emitting, and they have some interesting characteristics that we are going to talk about here. So in general, the cataclysmic variables, they evolve from long to short orbital periods and via loss of the angular momentum. The SW sextants ones, they present a very narrow range of orbital periods from 3 to 4.5 hours. That indicates that they are in the same evolutive stage, more or less the same age. And they are slightly above one important evolution period that's called the period gap, that starts from 3 hours to 2 hours when the angular momentum is disrupted and changed dramatically. So those systems, they are just about to suffer this, and they are all in the same orbital, in the same evolutive stage. That could be important for the evolution of CVs in general. Another major characteristic of SW sextants is that they even though they have this huge rotating disk, this huge bright rotating disk, that we should observe in the spectra double peak emission lines just from the blue shift part of the part of the disk and the red shifted one. So you would have two peaks. But we observe only one peak, even the systems that we know they are almost, the disk is almost edge on, because they do have eclipse, but you don't only see one single peak in the emission lines. And also those bright emission lines, especially Balmer and Helio one, even though we have eclipses and you see the continuum of their system going away, the emission lines are still there, they don't vanish. And this implies that the emission is not coming from the center or the disk, it's coming somewhere a bit far from that central region. So that's the mystery of SW sextants and how to explain that. There are some complex models and combining two different things like imagining optically thick disks and extended hotspot region, or disk overflow with winds. And there is an elegant solution, that's the magnetic accretion. So how we could, with magnetic accretion, you could explain the emission lines are coming from the tiny accretion column. It is not being eclipsed during the eclipse of the disk. It's always there. It dominates the emission line, so we don't see the double peak because we have this major source of emission lines that is not double peak. It could explain the characteristics of SW sextants. A way of confirming that is direct evidence, detecting non-zero and variable circular polarization, and detecting the white dwarf rotation coherent signal in the photometry. But of course, it's a challenging measurement because we expect polarization values to be very low, not only because well, we don't know more or less, we don't know exactly the magnetic field of the white dwarf, it's not so strong, but you have this bright disk that is diluting all the emission. They are not bright systems. The brightest one is around magnitude 12. And the rotation periods of the white dwarfs in these systems are the scales of minutes, half an hour. And that's because that explains why in the 2003, we have 28 systems that had observations with circular polarimetry. And for most of them, we have not known enough precision to tell if they are actually polarized or not. Have something consistent with zero, a couple of objects that have something different from zero, but that's it. So we start a campaign to observe SW sextants with the ERJ pole and LNE in Brazil. And here we observed 6 objects. We try to keep the exposure time the shortest possible, but not losing so much the precision. And taking time series of up to 6 hours, maximum can. During the data reduction, we had to be very careful. We studied all the objects in the field to discard any possible contaminations or systematic. So you see some of the data we could not use from that analysis. And we searched for periodicity, so for the modulated circular polarization, and also for some coherent modulation here in the photometry. And we are going to show the significant signals we got. So for the first one here, we have a strong modulation here in the period, in the photometry, something around 15 minutes. And the direct evidence of a magnetic field that would come from circular polarization. So we have a time modulation here, but with a significant peak here around 11 minutes for this object. We also have for the SW sextant star, the object that names the class. We took out the eclipse and we also could find a period here in the photometry, something not so significant, but it's still here in the circular polarization. For this one, we see the photometry. We got something also in the linear polarization we show here. For this one, we have a strong, found a strong period in the photometry and something indicating something, the circular polarization, maybe could benefit from more data here. LSPEC, that was an object that had previous measurement, we confirmed that. And for this one, the brightest one, so we see the error bars are smaller and everything, the signal is much stronger. We also had to understand all those peaks and see each peak is relevant here. And this is the last one that we also found a strong signal. So in summary, we reported a possible modulated circular polarization for 3 objects. We found with less significant periodicity for 2 objects here. And we confirmed the previous value for the previous detection for this object, but with a different value from the reported earlier. In conclusion, we interpret those periods as a spin period of the white dwarfs, and our polarimetry results, they indicate that 15% of SW sextant systems have direct evidence of magnetic accretion. And for more information, you can just take a look in this paper that Isabel just published. And it's really there are a lot of details there about the careful analysis that she had to do to confirm these tiny modulations we found. Thank you very much.